Okay, so today what we're going to do is look at linear systems and have a bit of a review of matrices and some of the fundamental properties of matrices and how we actually go about operating and using matrices. And then we're going to look at a process for finding the inverse of a linear system known as Gaussian elimination. The version of Gaussian elimination we're going to look at today we're going to call naive Gaussian elimination, because if you actually use this in practice, you'll often find situations where it won't work. We'll go on to actually figuring out how to remedy that problem when we look at it tomorrow. Okay, so very briefly then, we're approaching the end of Engineering 1060. Let's have a quick look at what the things are that we've done. We've looked at root finding, and we looked at a couple of different types of methods for doing that. Bracketing methods and open methods. You need to understand what the difference between these two general classes of methods is, when you might use one over the other, what the weaknesses and what the strengths of these two different categories are. Within bracketing methods, we looked at bisection and false position. You need to understand how those things work. You may be required to find the root of some equation, at least some approximation in the exam. Likewise, for open methods, how do they work? What's the difference between Newton-Raphson secant and modified secant? In what ways are they similar? Okay, so you need to make sure you go back to understand all that. Some of these methods will always converge on the root that you're looking for. Others sometimes won't. Which ones will, which ones won't? We also looked at the MATLAB built-in function f0. Then we looked a little bit at curve fitting. So we reviewed some very basic statistics, mean, standard deviation. We looked at fitting straight lines to data and coming up with this coefficient of determination, r squared, which gave us some sense of whether the curve that we're fitting is a good fit or not a good fit. But remember, this doesn't tell you everything. And for example, we had a look at an example in the lecture where if we mindlessly fitted a curve and looked at the result, we actually got quite a good value of r squared, but the results are unphysical. Okay, so you don't just look at the number, you actually go back and look at the result that you've got out and say, well, does this mean something, or is this just kind of like way out? So you need to use your judgment in cases like that. There's no hard and fast rule as to say whether this is a good fit or a bad fit. For the situation you're looking at, you've got to understand what the physics of the situation is and understand what your result is telling you. Is it physically meaningful? Is it possible even? We then looked at how we can take a couple of different types of models, exponential model, a power law model, and a saturation growth rate model, and linearize these things to effectively do a least squares best line fit. So we might take logs, we might take inverses of these things here, but we can come up with an equation ultimately that looks like a linear plot where we can do the straight line curve fit to, or best fit to, and then we can convert back into the other coordinates. Okay, so the actual models themselves aren't linear, but we can convert them into linear models. You need to know how to do that. We then looked at, well, okay, if we've got our best fit curve, we can interpolate data values at any point along this curve. We can also extrapolate. You need to know the difference between interpolation and extrapolation. When is it safe to do either of these things? When is it a bit risky to do some of these things? What are some of the risks in doing them? And we also looked, of course, at the inbuilt MATLAB functions polyfit, which allows you to fit a polynomial, a best fit polynomial to some data, and polyval, which then allows you to calculate the value anywhere on that polynomial. Again, you can interpolate or extrapolate. That's up to you as to exactly what you want to do, but you need to know when it's safe to do what. We then looked at numerical integration. So the trapezoidal rule, we said a few things about the truncation error there. There's a formula for that. And importantly, the composite trapezoidal rule. Fitting one trapezoid to your data that you're trying to integrate is not, generally speaking, going to give you a very good result unless you're trying to integrate a straight line, in which case you know the answer already. What do you do when you have unequal segments? Can you use the composite trapezoidal rule? The answer is, of course, yes. We then looked at the Simpson's rule, the 1/3 rule, which is probably the most common way of integrating things, and the 3/8 rule. And remember, there was a pattern in the 1/3 rule that looked like 141 for each pair of intervals, and that's how you summed the function values up. And for Simpson's 3/8 rule, the pattern looked like 1331. And this thing is repeated when you do these things in a composite sense. And you should also need to know when you might want to use these two things together. And we looked at composite Simpson's rule, of course, as well. The last topic that we looked at were ordinary differential equations. And we saw that the fundamental method in integrating ODEs is Euler's method. And this, in some sense, forms the basis of practically any other integration method you want to think about for ordinary differential equations. Personally, I think you should just remember Euler's method. It's such a simple thing to remember, and once you can remember that, you can kind of like figure out what the other things are as well. So Euler's method is the new value of my function is equal to the previous value plus the right-hand side, which is the slope, evaluated at the beginning of the step, TI, multiplied by the step size. New value equals old value plus slope times step size. That's Euler's method, and most of the other methods flow on from the use of Euler's method in various combinations. Now, I've had a couple of people come up to me with the assignment looking at using Euler's method to integrate the equation dA dt, where that is the function that describes the rate at which the arrow C is changing. You can actually do that. It's actually kind of interesting in this case is that the function, that dA dt in the assignment, is actually only a function of time. It's not a function of time and the area. So in other words, it's like integrating this thing here where our right-hand side now is just a function of time. The only problem with doing that is Euler's method, in effect, for an integral like this, is saying, okay, I'm going to start here and I'm going to estimate the next little bit of thing that goes into my integral as a rectangle. And then I get to whatever point here, then I'm going to do another rectangle. So it's less accurate than the trapezoidal rule. Okay, the error involved in using effectively an Euler step in that equation means it's less accurate than the trapezoidal rule. And so you may want to think about whether that's the best thing for you to do, or whether you should go away and integrate that with the trapezoidal rule or the Simpson's rule. Now, the thing you need to also be aware of is you need to look carefully at your data. You'll actually find if you go into that data, it's not evenly spaced. Mostly it's 1 year apart, but there's a few gaps in there. So can you easily apply Simpson's rule? What's the best approach? So I'll just leave it at that. We looked a little bit at the error analysis and provided a rough order of the estimate. We looked at programming the Euler's method function, and we then looked at a number of other different ways of looking at ODEs and integrating ODEs, and in effect we saw that the things like Hoyne's method, the midpoint method, even the Runge-Kutta methods, the only way they really differ is the way in which we're calculating this right-hand side function. So remember, with Hoyne's method, we take a guess at the beginning, do an Euler step, get to the end, then make an estimate of the slope at the end, and we average those two. With the midpoint method, we do something a little bit different. We take a half step, use that value of the right-hand side at the half step, and then need to go back to the beginning and integrate a full step. So you need to understand, at least conceptually, the differences between those things. And then using the ODE 45 to integrate things. Okay, that's a summary of the unit. We'll have another review of the whole unit next week. Matrix, don't forget too, your assignment is due. I think it's Friday at 6 o'clock, if I'm not mistaken. So hopefully you've all made a very solid start and you've pretty much done it, because it will take you a bit longer than you think. Let's just go over a brief overview of matrices. I mean, MATLAB is all about matrices. Could you please close the door up there, guys, when you come in? And one of the powerful things about MATLAB is matrix operations are really nicely done. You can just say, I've got a matrix A, I've got a matrix B, I want to multiply them together. You don't have to do it on an element-by-element basis, like you'd have to do in practically any other programming language. So how can we actually create a matrix? Well, the simple way of creating matrices are given by examples like this. There are functions like line space that will evenly space points. Well, these are actually going to be vectors, all of these examples here. And various different ways of filling numbers into matrices. Matrix addressing is important. So we have a matrix here which has got 2 rows and 3 columns. So the first index is the row number, and the second index is the column number. And it's very easy to get those two things mixed up, and if you do that, everything will be a mess. Okay, so you've got to keep it in your mind continually. The row number is the first index, the column number is the second index. And there are various different ways of looking at things. So B11 is just the element that's in the first place. So B11, in this case here, would be 1. B1 to 2, 1, means I want to take the first and the second rows and column 1. So that would be a vector that looked like 1, 4. Okay, B2 with a semicolon means I want to take all of the columns, but I only want to look at the second row. So that's going to be 4, 5, 6. Okay, the nice thing about MATLAB is you don't actually have to use numbers. If you've got vectors, or if you've got variables which have things in and you want to put these into matrices, you can actually replace these things with variable names, provided it makes sense from a syntactical point of view. So if you know that I, you're looking at element I, you can just say BII. And that'll give you the ith diagonal element of your matrix. Arrange more things here. The only thing I really wanted to talk about today was this idea of augmenting matrices. Okay, so what you can do is if we've got these two matrices, A and B, let's just write them out here, 1, 2, 3, 4, that's A, and B is equal to 1, 0, 0, 1. You can augment them. And what does that mean? Augmenting them means sort of bolting them on together. So there's a couple of different ways we can do that. So if we say aug AB equals, AB, that just equals 1, 2, 1, 0, 3, 4, 0, 1. We end up with a matrix that has 2 rows and 4 columns. Likewise, if you put a semicolon in here, we're going to augment them vertically rather than horizontally. So that then is going to end up with something that looks like 1, 2, 3, 4, 1, 0, 0, 1. So it's going to have 4 rows and 2 columns. Why is this interesting? Well, we're actually going to use this today in our Gaussian elimination. Okay, so you just need to know that you can actually do that. There's a whole ton of built-in functions for matrices in MATLAB, and certainly I'm not going to go through all of them today, but the ones that you probably will need are the following. Size. If you pass a matrix in to the function size, it'll tell you how big it is. It'll tell you how many rows and how many columns. That's really, really important. Often, if you want to write a function that does something, like maybe calculates the inverse of a matrix, but you don't know how big the matrix is going to be beforehand, when you go into that function, the first thing you want to do is, okay, what kind of matrix have I been given? How big is it? Are the number of rows equal to the number of columns? If they're not, then it's not a square matrix and I can't find the inverse. So you do that error checking. So size is a really important function in MATLAB. Length is a similar one. Length is the maximum value of m and n, effectively. In other words, if the number of rows is bigger than the number of columns, it'll tell you the number of rows. Alternatively, if the number of columns is higher than the number of rows, it'll give you the number of columns. This is important sometimes when you're coming to do things and you need a big block of, you want to pre-allocate some space and you want to know how much to pre-allocate. Maybe you're going to pad it out with some extra information. You need to know how big something is. So length is another useful function. The function I, for a square matrix, will give you the identity matrix. Okay, so you can actually call it a couple of different ways. So if you said I3, it'll give you a matrix that looks like that. It's the identity matrix. You can also specify that as I3, 3. So what does it mean if you actually specify it as, well, I want 2 rows and 3 columns? What kind of beast is that? Well, it's something that looks like this. The first part of it looks like a square matrix and the rest is just zeros. So what I does, regardless of the size of the matrix, the dimensions you pass it in, it makes all the diagonal elements where I is, the row number is equal to the column number equal to 1 and everything else 0. I think you've already come across zeros and ones. This just creates a matrix that is filled with zeros. This just creates a matrix that's full of ones. And another interesting one is if you just have a matrix, which is a 2-dimensional matrix, and you say A colon, It actually converts that whole thing to just one great big column vector. So it just concatenates such a, and now I can't quite remember whether it goes down the rows or down the columns, but I think it, yeah, you actually try it out for yourself. Okay, just some notation. And going through the lecture notes this morning, I see that I didn't even, well, the lecture notes didn't even follow their own notation, so I've gone and made a few little changes. Capital letters we will use for matrices. Lowercase letters we'll use for vectors, and you'll actually find in your mathematics and engineering degree that's a very, very common way of doing things. It just makes it easier to understand what's going on. So AX equals B, that's a matrix, that's a vector, that's a vector. Okay? Okay, and so, well, I've already said this, but for matrix elements, the syntax is A times row and column. So if A is equal to this thing here, A23 is in the second row, what's row 1, that's row 2, and the third column. Really, it's really important that you get used to that idea. I think you all know all this stuff, adding matrices or subtracting matrices. You can do it provided the matrices are the same size. If they're different sizes, it doesn't make any sense to do it. You can also multiply a matrix by a scalar variable. That just multiplies each of the individual elements by the same thing. So 3 times A, if A is equal to this thing here, is just each one of these elements multiplied by 3. I hope you all know about matrix multiplication, but we'll very quickly go through it. This formula here describes matrix multiplication. So if I want to look at the ijth element of a matrix C, which is the product of two matrices A and B, I calculate that by summing, when k equals 1 to n, aik times bkj, and I'm summing over the k index. So let's just have a quick look at that. If this is my matrix A, that's my matrix B, and this is my matrix C down here, the first element, element 1, 1, is equal to the first row of matrix A multiplied by the first column of matrix B. So that's 3 times 5 plus 1 times 7, which is this value here. Likewise, the very last one here will be the third row of A multiplied by the second column of B. But what that means is that if you have a matrix that's n by n, the only other matrices you can actually multiply it by have to have an n in this first index here. Okay? So when you're multiplying two matrices together, the size, the number of columns in this one has got to be equal to the number of rows in that one. Okay. You can do A times B, but you can't do B times A unless n is equal to L, in which case these are both square matrices. Now, another really important thing, even if you can multiply matrices A and B and B and A because it's possible, that operation does not commute, which means that A times B is not equal to B times A generally. Sometimes it can be, but often it's not. So you need to take that into account. I think you know about the transpose. The transpose, you just sort of swap the rows and the columns. You can actually do a transpose of a non-square matrix, but that turns a matrix which has 2 rows and 3 columns into a matrix that has 3 rows and 2 columns. So you're just swapping the rows with the columns. And in MATLAB, along with so many other things, there's an automatic transpose function which is just prime. So if you say, in MATLAB you'd say BT is equal to B prime. If you wanted to do this operation here, get BT from B. Okay, so that transpose operator is nice and simple one to use. I think you know about the identity matrix. We've discussed that already. It's got 1s down the diagonal and 0s everywhere else. The nice thing about the identity matrix is that A times I is equal to A. It's also equal to I times A. Okay, and we've already looked at the syntax for I. There is no such thing as a matrix divide in matrix arithmetic. What you need to do is calculate the inverse of a matrix. That takes the place of division. Okay, so the inverse of a matrix A is the matrix that when you multiply by A gives you the identity matrix. That's the definition of the inverse. A times A to the minus 1 is also equal to A to the minus 1 times A, which is equal to the identity matrix. And that's how you actually define the inverse. And there's no simple way of doing that. You've just got to go out and calculate that inverse matrix. There is an inbuilt function in MATLAB called ENV. You can also just say A to minus 1, and that will also give you the inverse. Okay, finally, we move on to linear systems, which is really what all of this matrix stuff, why we need to know about this matrix stuff. So you've probably discovered already that in engineering, often you'll end up with a set of simultaneous equations that you need to solve. Okay, and sets of simultaneous equations, provided they're linear, always result in a matrix system that needs to be inverted. Okay. Examples abound: electrical circuits, chemical reactions, fluid flow, heat transfer, factory processes, spring systems. We'll have a look at one of those today. They genuinely occur all over the place, so you need to know how to solve linear systems. So let's just quickly have a look at one. Let's imagine we've got this circuit here. We've got a voltage here and a voltage there, and we've got 6 resistors. And we need to calculate, well, okay, given that we know what this voltage difference is here, what V1 and V2 are, we know what all the resistances are, how are we actually going to calculate what the currents through each of these different parts of the circuit are? And why we want to do that? We want to know how much heat is being dissipated in different parts of the circuit, because we have to design the cooling system, for example. So we need to know where the heat's being dissipated. Okay, and also lets us know how much power we need to put in there if we want to operate this thing with certain currents. So we can model the circuit currents by using what's known as Kirchhoff's laws, and there's a couple of laws. The first law is, if we consider one of these node points here where the resistors join up, that the current flowing into this node has got to be equal to the current flowing out of it. In other words, you can't build up current there, well, unless that's a capacitor or something like that. But for just a normal junction, what flows in has got to flow out. And so what that means, and we need to define some sense of the flow direction here of the current as well, what's in and what's out. So that's, in a sense, an arbitrary decision, but once you've done it, you've got to stick with it. So this node here, I1 is flowing out, I2 is flowing out, and what's flowing in is I3. So this sum here has got to be equal to 0. You can't have a build-up of current, a build-up of charge. Okay, the second law is the voltage drop around a closed loop has to sum to 0. So if I look at what's flowing around this loop here, it can't be, the voltage drop around there has got to be 0. You can't have, in fact, it doesn't make sense to have a voltage drop that's non-zero. Around this loop here, the voltage drop has actually got to be equal to V1 minus V2. Okay, because that's where the current is, that's where the voltage is applied. So defining, I should have done this, defining this as the positive direction in terms of which way the currents are flowing, we can look at, okay, let's look at what's happening at node 2. Well, we know that there's a current, we're going to call it I12, that's flowing along here. Okay, it's flowing into the node, and we know that there's a current going in that direction, that's current I23, and there's a current going out here, that's I25. We know that what goes in, I12 minus I23 minus I25 has got to be equal to 0. Then let's go down to node 5. We know that the current between 2 and 5 is flowing in, the current going from 4 to 5 is flowing in, and the current going from 5 to 6 is flowing out. So that's what happens at node 5. Similarly for node 4, node 3, we then look at this right-hand loop, and we know that, okay, the resistances times the current in each of these things here has got to sum to 0. So if you actually just take into account the direction here, you end up with that equation. And finally, the current around this bit of a loop here has got to be equal, effectively that's got to be equal to V1 minus V2. So this is just the resistance times the current is equal to the voltage drop. Okay, but what we've got is now a set of linear equations that represents the physics of what's going on in here. So we've got 6 equations that have come up. So I don't know how many of you tried to invert a 6x6 matrix before, but I can guarantee you it would take a very long time, and you would almost certainly make some mistakes if you tried to do it by hand in a calculator. Okay, so even a very small system like this, you need something that's going to work a bit more effectively. So our unknowns in this case are the 6 currents. We know what the voltage drop is, we're told that, or we're given that, and we know what all the resistances are because we've designed the circuit. Okay? So, provided we can solve this for the 6 unknown currents, then we know the heat dissipation, we know the power requirement, we've designed our little circuit, we know what's going on. I hope I'm not about to lose my presentation. Another example, let's look at a bungee jumper, but now we're going to do something slightly crazier than we have done in the past. We're going to tie 3 of these bungee jumpers together with 3 different masses and 3 different spring constants in their bungee ropes. Okay, and we're going to let them all jump off, and they're going to bounce up and down, hopefully not hitting each other too much, and eventually they'll come to some kind of equilibrium position. Okay, so we got this first one here is tied to the top. Let's imagine that if we had these ropes that they were just tight but not stretched, we're going to say that that's the equilibrium position, not the equilibrium position, sorry, that's the x1 is equal to 0 position. So x1 is going to be the coordinate of this bungee jumper. We're going to say, okay, if we have this person with an unstretched rope, and then we put this person with an unstretched rope, his coordinate, her coordinate, is going to be x2 is equal to 0. This is just going to be our definition. Likewise for the third bungee jumper, x3 is equal to 0. So now we have to sit and look at this thing and say, okay, what are the forces acting on these 3 bungee jumpers? We're now going to let them do their jump, they're going to bounce around, and eventually they'll end up in an equilibrium position. So what's going to happen? Well, we want to know what that position is relative to this situation here. Okay, because this is the one where there's no force, no spring forces from the bungee ropes acting on them. So this bungee jumper, okay, something's pretty bad here. Yep. Aha. Where it chocks away. Okay. So when this person has moved from the x1 is equal to 0 position some further distance down, okay, and that distance there, well, we're going to call that distance x1. There'll be several forces acting on him. The first one, there's always going to be a body force. That's going to be equal to the mass times gravity. Because the equilibrium position was somewhere up here, and we pull down a distance x1, there's going to be a spring force acting upwards that's equal to k1x1. But there's 2 other bungee jumpers attached to him down there. What's that force going to be equal to? Well, we can actually not figure out what that force is, but that force is going to be equal to how much stretch there is in this second rope. We don't actually even need to know the mass of these guys here to calculate this one here. We can calculate that directly from how much stretch. So if the first bungee jumper's fallen down a distance x1, that means the second bungee jumper can fall down a distance x1 as well, and there'll be no extra tension in his rope. But as soon as that goes beyond x1, then there starts to become tension. So that distance there is given by x2 minus x1. So there's going to be a force equal to the spring constant on the second rope, k2 times that distance, which of course has got to be equal to the force pulling the second bungee jumper back up. There'll be a gravity force on him. Similarly for the third bungee jumper, he'll be able to go down a certain distance before that rope starts becoming in tension. That's going to be equal to x3 minus x2 times the spring constant. And finally, the last one, this spring force pulling him up and this body force pulling him down. So let's go through that. What does it look like? So those are the forces on the left one, the middle one, and the right one. We've just added all of these things together. Whoops. So what we're trying to find here now is what are the distances x1, x2, and x3. Those are our unknowns. We know all the masses. We know the spring constants. We know what gravity is equal to. These are the 3 simultaneous equations that we need to solve to understand this system. In order to do that, we need to write it like a linear system. Let's just go back. System. This is kind of a bit messy because our unknowns are scattered all over the place. So what we need to do is we need to group those unknowns in a nice, coherent way that we can actually look at what's going on. Okay, we want to be able to write the system as AX is equal to B, where A is some matrix, X is our vector of unknowns, and B is our right-hand side. And that's the system ultimately that we'll need to show. So this is what we've started off with. We want to write it in a form that looks like that. Well, I think you can see, or at least I hope you can, we just need to group the x1s in this equation, then the x2s and the x3s, and likewise just group everything together so that we can write it in this form here. So starting off with, well, expand the brackets, that's obviously the first thing you're going to do. Then group all the terms in x1 so we can see, and what we're going to do too is we're going to move, well, effectively move that across to the other side, but then swap sides. So we have k1 plus k2 x1, that comes from this term and this term, minus k2 x2, that comes from that term, is equal to m1g. That's our first equation. The second equation's slightly more complex. There's a term in x1 now again. No, we're going to keep these on this side. So it's minus k2 times x1. Oh, that looks like there's an error here. x2. There's something wrong with the signs in this example. I'm going to have to go back and look at them because those are both negative there, but they're both positive down here. So there is an error somewhere here. I'll have to check that one out. And then the final equation is k3x2 here and k3x3 there. There's something wrong with all of the signs on this. I apologise for that. I'll have to go through and look at these a bit more closely. Regardless, apropos of the incorrect signs, we will end up with a system of equations that looks like that, which is exactly the form we want. We've got some coefficient times x1, another coefficient times x2. Implicitly in here there's a 0 times x3. We don't need that because it's 0. Likewise, a coefficient times x1, coefficient times x2, x3, and etc. So our matrix system that we're trying to invert, that's A, that's B, and X is just the vector x1, x2, x3. Okay, that's pretty much what I said. Okay, so we've got a 3x3 system. You could actually do this by hand if you wanted to. It'd still be a bit fraught, but you could do it. For bigger systems, it just becomes too difficult. So what I'm going to say here is that I'm going to say small systems are things which have less than 3 degrees of freedom, less than 3 unknowns. Okay? Well, less than or equal to. Hey guys, if I don't mind you having a bit of a joke, that's fine. Could you do it outside, please? Because I really find it off-putting. Yeah? Okay. So, I'm sure you've all done these kinds of things in high school, eliminating the unknowns. In actual fact, for 2 degrees of freedom, or 2 unknowns, there's what's known as the graphical method, which is pretty simple. But before unknowns and above, you need to use matrix elimination or some other kind of matrix inverse technique. The nice thing, of course, is that these systems that you might develop here for large systems, they're also going to work on small systems. It's not restricted to the large systems. Okay, so let's have a look at an example of how we might use the graphical system for just a 2x2 matrix. Let's say we've got these two equations here. 3x1 plus 2x2 equals 18, and minus x1 plus 2x2 is equal to 2. Now you can actually rearrange both of these things so that we can actually solve them, say, in terms of x2. So the first equation becomes x2 is equal to minus 3 halves x1 plus 9. The second equation becomes x2 is equal to 1 half x1 plus x. You're just making these the subject of the formula in both cases. Then, just treating x2 as y and x1 as x, we actually just plot these lines. So this is y is equal to minus 3 halves x plus 9. Which is this line down here, and this one is x is equal to y is equal to 1 half x plus 1, which is this line here, and these two straight lines meet in a point. Now, in actual fact, If you did this in 3 dimensions, what you'd have is you'd have 3 planes. So you'd have one plane here, one plane there, and then some other plane that's going to hopefully cross perpendicular, and the solution would be that point, that single point where all 3 planes coincide. But that's much harder to actually understand and visualize. If you wanted to go to a 4-dimensional system, well, then you've got sort of hypersurfaces, so 3-dimensional hypersurfaces interacting, and I don't know about you, but I can't actually visualize that. So that's why you can't possibly use graphical methods for anything significant. Now, there are a number of special cases here that we really have to be aware of. The first is when these 2 lines are parallel. Okay, that means the lines never cross. In practice, what does that mean? It means there is no solution to those equations. There are no values of x1 and x2 that satisfy both of those equations simultaneously. Okay? The kind of like ludicrous case of that is when the lines are exactly the same. So in other words, all points along that line satisfy the equation. So you can't actually find a solution. Any solution along that straight line will work. There's another case too when the lines are almost parallel, just not quite. That system becomes what's known as ill-conditioned. And tiny, small errors in numerics can actually give you a completely different solution, not because there isn't a solution, but because the computer accuracy isn't sufficient. Okay, so let's now talk about Gaussian elimination, because that's really what we're after here. So Gaussian elimination is a way to find the solution to an n-dimensional linear system. There are 2 steps. You just need to remember that there are 2 steps. The first one is called forward elimination, and so we're going to get rid of some of the stuff that makes the problem difficult, and then backward substitution. So we go through the matrix in one sense and get to a point where it becomes easy to start solving it, and then go back the other way to calculate the values. So it's a multi-step process, but there are 2 blocks of steps. The first one is the forward elimination. The second block is the backward substitution. So the forward step eliminates the unknowns one by one, and the backward step substitutes the values in so that we progressively start calculating the final solution. I mentioned before, we're going to call this naive Gaussian elimination because the way in which I'm going to present this to you today means we can actually divide by 0. And in practice, of course, we know that that's going to cause us lots of problems. There is a nice simple way around this, but let's just have a look at the basic process first. Okay, Gaussian elimination, as we're going to discuss it here, operates on an augmented matrix, and that augmented matrix is going to be the matrix A with that column vector B, which is the right-hand side. Okay, and the system we're solving, of course, is that one there. And I've already said that. The augmented matrix is the horizontal concatenation of A and B. So it's this thing here in MATLAB syntax. So we're going to go through an example. This system here, I'm not going to read it out, you can look at that yourself. So the matrix A is equal to that, the matrix B is equal to that, and our unknown vector is that's X. And the augmented matrix, we'll just call it aug, is just equal to this thing here. Okay, so this is the right-hand side. Okay, we've just sort of stuck that onto the end. So let's have a look at this matrix, or this augmented matrix. What we want to do with this matrix is we want to somehow get these values, all those values before that lower diagonal, equal to 0. That's what we're aiming to do here. And we're aiming to do that by adding and or subtracting various amounts of higher rows so that we can eliminate these values here, make them 0. So we're going to start with the first row, and we're going to add some multiple of this, or subtract some multiple of this, to this row here, so that we can set A1 equal to 0. We then move down to the second row, or the third row, sorry, in this case. We're going to add or subtract some multiple of this first row to make this element 0. Once we've gotten all the way down to the last row, we then say, okay, let's move across to the next element we can get rid of. Well, in this case, there's only 3 things, so we're going to go to this one here. Now, we want to multiply. We've now changed this row here because we've subtracted some of this first one. what we want to do is we want to subtract some of this second row, or add some of this second row, to get rid of this element here to make this 0. And so we end up with a system where these are all zeros, and then we can start the back substitution. Okay, so we basically repeat those steps as I indicated until we've just got an upper triangular matrix. Okay, plus this extra bit here. Now you'll notice that in this notation here, I've got dashes here, and I've actually got a double dash here. It means that these coefficients are not the same as these coefficients because we've changed them. Okay, so we've gone from this step, we've done the forward elimination, we've got to this point here where everything's 0. What this last equation here corresponds to is A33 double dash times X3 is equal to B3 double dashed. Sorry, it's a bit of a mess. We can actually solve this equation directly for X3. It's just equal to B3 double dash divided by A3 double dash. And you can see already, well, there's going to be a problem here, perhaps if A3 double dashed is also 0. Okay. Once we've solved for X3, we can then substitute X3 into this equation here and calculate what X2 is equal to. Once we've got X2 and X3, we substitute X2 and X3 into this equation and calculate what X1 is. So that is the back substitution. Actually, it should be backward substitution, actually. Because of the upper triangular formulation, each new row only contains one extra variable. So that's why we can do this. So at each step of the row going backwards, we're calculating one extra unknown. So let's have a look at this system here. So we've got to start off with the forward elimination. So we start off with, okay, the pivot point is the point that we're actually going to, it's the leading diagonal of this thing. So we're in row 1, it's the point number 1, column number 1. We need to get rid of this value here. What we've got to do to get rid of that value there is we've got to multiply this equation here by 0.1 divided by 3 and subtract it. So effectively we're dividing by 30, dividing this one here by 30, subtracting it from this one here, and we end up with 0x1 plus this stuff. We're not going to go through the arithmetic here. Then we need to get rid of this value here. We need to divide this one by 10 and subtract it from here. Okay? So that then... so that means then that there should be a 0x1, not should be, but there's a 0x1 there as well. We've got rid of the x1. So we've done some of the work. Okay? Now, notice in this process that when we're multiplying these equations by numbers and subtracting them, we're also changing the right-hand side value. When we do this in an augmented matrix, that's, in a sense, automatically done for us. That's the beauty of doing the augmented matrix. So, after we've gotten rid of our first column, we've ended up with a system that looks like this. We've got zeros in these points. We now need to get rid of this point here, because it's the next under diagonal point. We're going to keep this one because it's on the diagonal, and that's fine. We now want to make this the pivot. We don't want to go back and keep using this one here, because if we subtract the right amount of this row to get rid of this point here, we'll add something back into the first point. We don't want to do that. Okay? So we have to use this row here because we already know that this one's 0. So it doesn't matter how much of this value here we add or subtract from this one, it's not going to change it. So we now use the next row down to pivot. So what we're doing is we're multiplying this equation here by that divided by that, and then subtracting it from this row here. And that then gives us this system here. So we've got zeros on the under the diagonal, and we've basically finished our forward elimination. Okay, we can now start back substituting, because if you look at this last equation, it's just 10.012x3 is equal to 70.0843. So we can calculate x3 just directly. Okay, 7.0003. Once we know x3, we can go up to here, substitute x3 in here. So we've got this coefficient here, the negative 19 goes there, and the value we've just calculated there goes in there. So x2 is just equal to negative 2.5. We've now got x3 and x2. We can go up to this equation, substitute x1 and x2 in here, and calculate x3 equal to 3. That is Gaussian elimination. Okay, we didn't do any pivoting, in other words, changing rows and elements. It's naive because in this whole process it's entirely possible that we might be dividing by 0. We're going to fix that up next time round. So, what have we learned today? We've looked at matrices in MATLAB. We've looked at how to represent a problem as a linear system. And we've looked at a very naive form of doing Gaussian elimination, which will allow you to invert matrix systems.